about scatter plots, and we talked about how to know if it's a good linear model by that correlation coefficient R. And then we talked about writing the equations of the scatter plot, or of the line best fit, which we can do by hand, and we did one just to practice, really more reading those formulas and understanding them than anything else. But mostly we use the calculator for those. So we're going to continue talking about that regression line a little bit today. There's a few other things that we can look at on that. The first one is called a coefficient of determination. It's your R squared. Remember, every time we did the linear regression and it came out with our A, B, R squared, and R, we were looking at R. The R squared is on there as well, but it's the same as if you just squared your correlation coefficient. So it's given on our calculator, or we can easily find it by squaring. It's not something we use a whole lot because we already have that R value, but it's essentially telling us the percent of the variation in our Y values that's explained by the line. Okay, what we mean by that is if you think about a line, okay, every point on that line has a different Y value, correct? So the Y values vary. If it's a perfect line, then 100% of the reason my Y's vary is because of that line. If it's not a perfect line, these Y's are different. So we're basically saying what percent of that variation is because of the line. R squared will give us something between 0 and 1. 0 being 0%, 1 being 100%. So just kind of like our R value, if it's close to 0, it's saying there's no relationship. Or none of the variation is explained by the line. That point doesn't follow the line. If it's 1, it's 100%, so it's a perfect explanation. When we talk about deviation, it just means how values are different from the mean. So explained is variation that is due to the regression line. Okay, if we have a set of values, we know that not every value is going to be equal to the mean. So that's the explained variation. We expect some variability if we're looking at points on the line. Unexplained is anything due to something else. So other factors. It's not what we would expect with our regression line. So we are just going to use our calculator to get an R squared value and talk about that. So this is, I think, a table, we've used this data a few times. So we have our X and our Y. So we are going to put all of these into our L1 and L2.
I love when my diagnostic is actually on.
Yeah, that's So remember, you enter this in L1 and L2, and then you go into your stat, calculate number 4. Did anyone not get the R and R squared on their screen? If you don't have it, you need to turn the diagnostics on. Does anyone need help with their diagnostics? Eventually we'll probably have it turned on every calculator in here, but until then. So when I look at this, the R squared and the R. So R is the coefficient of determination, what we were doing before, 0.7728. That's our correlation coefficient. So then the R squared, if you square it by hand, double check. If you take 0.7728 and square that, doesn't it give us the other number?
Mm-hmm.
Yeah, so it's already given the square. If you square it by hand versus writing down the R squared given, it may be slightly different due to rounding error. So if I write down the R squared for my calculator, it's that, versus if I typed in 0.7728 squared, I would get 0.5972. So slight difference, but that's only due to rounding. So you can either square it by hand or just use our calculator. So what that means, that is my actual coefficient of determination, and just like everything else, if you forget what a coefficient of determination is, how do you figure it out? Formula sheet. You can look and it tells you the coefficient of determination, R squared, measures blah blah blah. So it tells us directly on here. So the interpretation, everybody look at your formula sheet so we can talk about what this means and how you would figure it out if you were in a test and you forgot. So that is the last bullet in the chapter 4 section. So it tells us coefficient of determination, R squared, measures the proportion of total variation. So I could say the proportion, or a percent, 59.73% of the variation. Okay, back to my formula sheet. It says in the response variable. Which of these is the response?
The time.
The Y, yep. So in the drill time. Okay, and if I look back at my formula sheet, it says is explained by the regression line. That's all it's saying. So almost 60% of our variability is expected with the line. The other 40% is being caused by something else. The next slide is just kind of showing you, just like with R, the closer R is to 1 or -1, the better the line was. Same thing with R squared. The closer it is to 100%, the better your line. So this is showing a set A. We can see that line was almost perfect with our points. That's a case where it was like 99.99% of the variability was due to the line. B is a little less accurate. That one was a 94.7. C, it doesn't even look like that's a linear model at all. That one was only 9.4%. So it's just kind of showing you the smaller your percentage, the more spread out your points are, is essentially all it means. All right, the big thing that we're looking at today. So this was kind of the first little piece, but not all that significant. The next thing we're looking at is the residuals. We talked about residuals yesterday. What were the residuals?
Difference between the given and the found.
Right. So if you took your observed value, the value from our table, minus what our equation said, that gave us the residual. Remember, the regression line is basically trying to make those residuals as small as possible so that the true value is close to what we would get from our line. We will look at residuals in terms of the scatter plot And if we plot our residuals, it actually tells us some information about the original data. So residuals can tell us if a linear model is good. The first way, we're just deciding if that linear model is appropriate. We can check for whether the variance is constant, and we can look for outliers. So those are the three things. If the linear model is appropriate, okay, we shouldn't see any patterns in our residuals. If we graph our residuals and they all start out really high and then get really low, okay, that's an issue. Because what that's telling me is, at first, my real values were way higher than my line would have said, and then it ended where my real values were much lower. So that linear model wasn't really consistent for my data. We want the variance to be constant. If we plot our residuals and we get something like this, that means it was a good model at first, but as time went on, that line became less accurate. So that's an issue. And then we can look for outliers if there's a point far away from the rest. So this is a little bit easier to understand when we look at the actual plots, like we're going to in a second, but we're just going to jot down a couple things here. When we're looking at the residuals, no pattern means it's linear. So we want to be able to graph our residuals and see no patterns at all. The reason we have to do this is that the correlation coefficient can be a little misleading. So it can imply a linear model when one really doesn't exist. Residuals check for this. So it's just a second way of checking ourselves. We can check our correlation coefficient against that table too, but we can also look at our residuals. And the whole reason is to make sure that we're not saying a linear model works when it really doesn't. So I have a graph just to kind of show you. This first one is a residual plot. That one's a good plot. I just have random points. Okay, this is different than the regular scatter plot. These aren't the true points. Those are your residuals. If you took every value on your table minus the value your equation gave you, and plotted those results. So no pattern is good. This one is bad because we can see that the beginning points, my observed value was much higher, and then it was low for a little bit, and then it started being higher again. So when we see a shape like a parabola or something coming out of that, that's probably not a good sign. That's something that's not very linear. So I want to take a look at a set of data. I'll go ahead and mention this graph before we do the next example. So this is just showing us a couple other things. This one, if we look at this, does it look like a good line of best fit? Yeah. But if we look at the residual plot, what we can see is this violates what's called constant error variance. It means over time, my points are getting further and further away from the line. And we can kind of even see that here. This line started off as a really good model, but by the time we get to the end, the points are further away. So this is saying that a linear model may not be the best option here. These are some other issues. So this one shows an outlier. You can see your residual plot, all the points are pretty close together, but you have one, or sorry, this was the original scatter plot. We see this point out here. Maybe we couldn't tell if it was an outlier there, but when you look at the residual plot, you can see all my residuals are here and we had this one far out. So those points in our scatter plot that are kind of on the line, we're not sure if it's an outlier or not, it becomes more obvious when we look at the residual. So the things we're looking for, is there a pattern? Patterns are bad. Is that getting wider over time? That's bad. And do we have an outlier? So let's look at the residual plot for our data. Okay. I did not do it on my board calculator, but that's okay. So we have, in order for your residual plot to work, I need to stress this, you have to do the linear regression. So it's not just a matter of entering your data in, you have to go through and do the stat calc number 4. If you don't run that, it's going to give you an error message. So you have to do that, which we already did on the previous example. So all of us should have that entered in our calculator. Now we are going to go into our stat plot. So if you hit the second y equals, that takes us into plot number 1. Okay, go into plot number 1, turn it on to a scatter plot. Okay, and then you see the X list. All right, when you go to your Y list, we need to change that Y list. So X list is still going to be the L1. When you get to your Y list, we are going to push second stat. And this is giving us a list of other variables that we can use. And it should be at the bottom of that list, number 7, it says resid. That's our residuals. So, the X's are L1, the Y2 is our residuals. And you get that by going into second, and then your step. Alright, so then we can look at our graph. You will need to go to zoom 9, so it will zoom to where your data is. And we should have something that looks like, I should have done it on my calculator up here, but that calculator makes my computer slow for some reason, Alright, we see something like this. So, is that linear model good? No. What's wrong with this? Yeah, it's getting more spread out over time. So this violates the constant error variance. That means my linear equation was pretty good at the beginning. At the beginning, most of my points are pretty close to that. But as time is going on, it's becoming less accurate. And is that too much of a surprise? When we looked back, what was our R value for that data? 0.77. 0.77. So is that super close to 1? Not really. We said only like less than 60% of the variation was due to the line. So we had some factors back here that probably made us curious if it was a good model. This is telling us it's not the best. It's good at first, but as time's going on, it's becoming a worse model. Does that make sense? Second thing I want to talk about with this are if we have influential observations. So the least squares line is not resistant. If you have some outliers, it really throws off the entire equation of the line. So if I'm looking at this and I wanted to know, are any of these points influential? Would they change my line a lot? Okay, can we agree that all three of these would be outliers? Yeah, none of those really follow the general trend. So they're all outliers. Which of them will have the biggest impact on a regression line? So 3 is going to have a big impact. Why?
It's lower down.
Mm-hmm. So this one is, we would call it influential. Okay, not only is it an outlier, it goes against the pattern. Right, it is the most influential one up here because with all these, as time goes on, my points are increasing and case 3 drops it down. So that is probably the most influential point here. Is 2 influential?
Not as much.
It's pretty much lined up.
Yeah, it's an outlier, but it's following the pattern. If you thought about your line of best fit and you drew that, that point is pretty much on my line. So it's not going to have much impact, if any, on my equation. All right, this one, what do you think?
Not influential. No, it would be because it's way higher than everything else.
It's
but it's
higher.
lower down on the exponential.
But it's following the pattern, like it's increasing, but it is going to be influential. It's going to make my line come up a little bit. But is it going to have as big of an impact as case 3?
No.
No, because case 3 is going to really goes against the grain. This one is still somewhat following the trend. It's just a little bit higher than the others. But out of all of these, 0.2 was the least of a problem. 0.3 was the biggest issues. Any questions?
Did you say that you saw a graph of dots going down, just like starting at top of everything, is that bad?
With your residuals, yeah. If you see any pattern at all, that's probably an issue. You want just basically random points when you're looking at residuals. Okay, so let's look at this. We've been dealing with that drilling data. If we have an additional point added of 312.9, we want to know if it's influential. Before we do anything, let's jot down the equation of that line. I didn't write it down before. It was, if I ran my regression again, stat calc number 4. So the original line So now let's go to our stat edit, and we're going to add one more point down at the bottom of this list. So the x is 300, the y is 12.49. Does that seem like it's an outlier?
Yes.
Yeah, before my biggest x value was 190, so 300 is definitely an outlier. And let's do the linear regression again. So, can we all agree that the new point is an outlier. We think it is. Look at your residual graph. So we ran our new regression. So if you just go into your stat plot, it should be set that your x is L1, your y is your residual. So if you go to zoom 9, does this look different now? Yeah, our residual plot, and then you've got this point out here. So definitely it's an outlier. We can see that. Is it influential? So obviously any outlier is going to change your equation some. If it's influential, it has a big change to your equation. So my slope changed from 0.01 to 0.02. Is that a huge change? Not really. My y-intercept 5.5 to 4.4, is that a huge change? No. So this one is not influential. It changed my equation some, but not drastically. Alright, so are we kind of understanding like what influential means, what outliers mean, how we can use the residual plot to check for that? I really just wanted to let you guys practice one more. So here's a new set of data. I want to decide if this is linear. Let's use our residual plots to decide it. So we'll look at a couple different things. We'll look at our correlation coefficient and our residuals. So we put it all in L1 and L2. If we run the correlation coefficient, then we look, so our linear regression, what is the R value?
-0.9941.
Okay, so does this make us think it's linear? Yeah, that's very close to -1, so we're thinking probably a strong linear relationship. Let's graph our residuals. So if you go into your stat plot, everything should be set. By the way, if you need to go back to an original scatter plot, you'd have to change your y's back to L2, just as a heads up there. So if we look at our zoom 9, what do you see in these residuals?
They follow a pattern.
This is definitely a pattern. So this made us think it was good. Our residuals are saying not really. It means at first the real values are higher, then they're lower, and then they're higher again. So we're seeing a pattern here. Basically, it overestimates at first, then underestimates, then over again. So this is not a linear model. That means there's some better type of equation out there. Linear is not my best bet. Any questions for me? So this stuff is pretty much all based on the calculator. We're really doing no calculations by hand. So I am giving you class Monday to work on this. So you have homework. You can get started, but please don't feel like you need to take it home and work on it over the weekend. You should have plenty of